Hello students, as in previous videos we have studied about work and energy individually. Now in this video the topic is work energy theorem. So basically we are going to discuss a relation between work and energy of a body. So if I talk about the statement directly, so it states that work done by the net force acting on a body is equal to the change produced by the kinetic energy of the body. So the statement of this theorem is the work done by the net force acting on a body is equal to the change produced in the kinetic energy of the body. Now to understand this statement, we assume that we have some object, right? We have some object A with mass m, which is moving with some initial velocity, that is u, and now a force act on it in the same direction. Okay, this is the force that is pushing it in the same direction, or it is taking it or accelerating it towards the right direction. So now because of this force, some work is done by this force on that object A, and as a result of that force or that work, the velocity of the object will change. Now after some time, let the position of the object is this, and now it is moving with some different velocity, that is v. Since the velocity of the object get changed, so its kinetic energy also gets changed, because we know that kinetic energy depends on velocity and its value is half m into velocity ka square. So in case 1 it is half mu square, and in case 2 it is half m v square. Means after changing of velocity from u to v, after certain time it becomes half m v square. So because of this force acting on that object A, there is some change in the kinetic energy of that object. Now this change produced in the kinetic energy of the object is equal to the work done by this force. That is the work energy theorem. So work energy theorem states that work done by the force, right? This is the W, work done by the force on an object is equal to the change in kinetic energy of that object. Now this is the statement. If we want to prove it, so there are two possibilities, that the force acting on the object, it may be constant or may be variable. So we will prove it for both cases. First we will prove it for a constant force and then for a variable force. I am dividing this page into two sections. In section 1, that is the left section, I am going to prove it for a constant force. Means this is the proof of work energy theorem when a constant force is acting on that body, and on this side I am going to prove work energy theorem for a variable force. So first we will talk about constant force. The case of constant force, suppose a constant force F is acting on a body of mass m, right? The force acting is F on a body of mass m, and it produces an acceleration in it. Because of it, the acceleration produced in the body is a, this we are assuming. So after covering distance s, because of this force the body will be in motion and it will cover some distance. Suppose the distance it cover is s, and after covering this distance s, after distance s, the velocity of the body changes from u to v. Initially its velocity was u, but after covering this distance s, its velocity is v. Then in that case, from third equation of motion, we can write that v square minus u square is equal to 2as. This I am writing by using third equation of motion. Now multiplying this whole equation by the factor m by 2 or half of m, I am going to multiply this equation by the factor half of m, then we get half m v square minus half m u square is equal to half m and 2as, right? So 2 and 2 will be cancelled out, and this m into a, this mass into acceleration, will be the value of force as per the Newton's second law. So I can write half mv square minus half m u square is equal to F into s. And as per the definition of work done, the product of the applied force and the distance covered, this is equal to the work done on the body by the net force. So this is final kinetic energy, I am writing it as kf, minus यहाँ हमने initial velocity लिया है, so this is initial kinetic energy, and on right hand side force into distance is the work done W on the body by the net force. And this shows that the change in kinetic energy, left hand side is the change in kinetic energy, is equal to the work done on the body by the net force. So this is how we can prove work energy theorem for a constant force acting on a body. All right, now we are going to prove it for a variable force. So suppose a variable force F vector, okay, this is a variable force F vector, act on a body of mass m. A variable force F vector act on a body of mass m, and because of it, that body displays, or it produces a displacement of ds vector. But this displacement is in the direction of force. The force that we are assuming is giving displacement of ds vector to that body in the same direction. That means the angle between force and displacement theta is equal to 0 degree. So this is we are assuming. Now in this case, the small work done dw can be given as the dot product of the force and the displacement vector, that is f dot ds, and we solve it and get f ds cos theta, where theta is 0 degree and cos 0 has the value 1. So dw, or the small work done because of this variable force for small displacement ds vector, will be f ds. Now by applying Newton's second law of motion, we can say that the force is equal to mass into acceleration, and acceleration is actually the rate of change of velocity, that is dv over dt. So we are going to put this value in the above equation, that is dw is equal to f ds. So by substitution we get dw is equal to m dv over dt ds. We can write it as m dv ds over dt, and again ds over dt is the rate of change of displacement, that means it is the velocity. So dw can be written as m v, ds over dt is v, mv dv. All right, dw is equal to mv dv. Now if we applied the force, it increases the velocity from u to v. The force F vector change the velocity or increase the velocity from u to v, then the total work done on the body can be obtained, the total work done can be obtained from this equation by integrating this small work done within the limits of u and v. If we integrate it in the limits of velocity from u to v, we can get the total work done. So total work done on the body will be W is equal to integral dw. Now integral will be done in the limits of u and v because it is in the terms of velocity. So u and v, mv dv. Mass is constant, we take it outside the integral, m u to v integral v dv. Now integral x dx, we know that integral x dx is x square upon 2. So here integral v dv will be v square upon 2, that means m v square upon 2, and the limits are u to v. So w is equal to m. Now we are going to apply limits as final limit minus initial limit. So it will be v square upon 2 minus u square upon 2. Now the first term is half mv square, which is the final kinetic energy, and the second term is half mu square, which is the initial kinetic energy. So again here we have proved that the work done is equal to the change in kinetic energy. That means the difference between final and the initial kinetic energy, this is the change in kinetic energy of the body, and it is equal to the work done on that body by the force that we are applying. So this is how we can prove work energy theorem for variable force. So that's all for the work energy theorem. The statement is the work done by the net force is equal to the change in kinetic energy. Now there are two possibilities, force can be constant or force can be variable. So accordingly we have to use the relations, the value of force, and prove the theorem, that is kf minus ki is equal to w. That means change in kinetic energy is equal to the work done by the force on that body. That's it for the video. For further videos, stay tuned and keep studying. Thank you.